my talk is called "Oh, All the Things You'll Traverse," and it's not really about philosophy, maybe a tiny bit, but yeah. And as a quick motivation, like a lot of people ask me, like, what does the CATS library actually do? And I want to give like a quick overview of what we can do. And one of my favorite topics for actually like motivating usage of something like the CATS library is this small thing called traverse. And because this is like a beginner's talk, I'll try to build it up from the very beginning. So yeah, a very quick about me. I work at CodeCentric. I organize Scala Düsseldorf and Idris Düsseldorf meetups. So if you're ever in Düsseldorf, check it out. Please come by. If you want to give a talk to me. And I'm also a maintainer of CATS Effect, CATS MTL, and Outwatch. And I'm really enthusiastic about FP, and I want to share it with as many people as possible. And seeing all of you here is it's pretty crazy, and it's intimidating and awesome all at the same time. So. Yes, on the agenda we have type classes and then monoids and functors and traversals. So these may sound a bit intimidating, but I'm gonna try to like explain them from the bottom up. Right, so who here has heard about type classes? Oh, that's a lot of, who has used them like extensively? Okay, that's great. So I won't have to do that deep an explanation. So type classes, they give us this thing called ad hoc polymorphism. And it's a different kind of polymorphism from what a lot of us know as subtype polymorphism using inheritance. And type classes themselves, they don't work on actual values or on instances of values of classes, for example, but they work on types themselves. That's why they're called type classes, right? And in theory, they're very similar to OOP interfaces or traits in Scala. And as of right now, there is no language feature that allows us to do like type classes as a native feature in Scala. But that actually might change in the future, so who knows. Right, so I'm going to just give you a very quick example of a type class. And I'm going to use this library called Simulacrum, which makes it a lot easier, and it's basically emulating type class as a native feature using macro annotations, right? So this little thing at type class that basically tells us this is like this thing is going to be a type class, and we use type classes as traits. You can see the similarity again there, and this type class is called show and has an abstract type t and a single method called show. And this show just takes the value of t and returns a string, right? So basically it's, if you have an instance of this show type class, then it means that you can convert a type t to a string, right? So basically, this just means that we can convert a type t to a string. And to actually implement this, we don't like extend a class from an interface. What we do instead is we create a so-called type class instance, and this looks something like this, right? So in the first example we have here a show type class instance for string, and it's of type show string, and we can just create it by just instantiating this show trait for the string type. And because string already is a string, the show method just gives it right back. So it doesn't do a lot. And then, of course, we also have show integer or show int. And because Scala 2.12 allows us to call single abstract method types, SAM types, using a lambda, we can just say underscore dot toString. So if our type class only has a single member, we can actually implement instances really quickly. So this is just how it works. And then if we actually want to use it, so we can create something like this. So this empty if false method takes an abstract type t and constrains it using something called a context bound, right? So this double colon show basically means that if you want to call this empty if false method, make sure that the t you're giving it has to have an instance, right, of show in scope, right? And that's what we do above. By creating this implicit value, we create a type class instance for show. So after we define this instance for show string and show integer, we could now call this empty if false method with integer and string as our type t. And if we were to try this with any other thing, it would complain that, hey, you don't have a type class instance for your type t, right? And this function doesn't do anything crazy. It just checks if this predicate function f is true, and then it will either return the string that's called by using this show method, or else it will just return an empty string, right? So this is a very, very basic example that doesn't really do anything useful. So let's look at something a bit more useful. And I promised monoids, and this is the monoid type class, and it is really, really cool, but it doesn't look like much, right? So we have this thing called the empty method, which will return some type t, and we also have a combine method that takes two t's and returns a new t, right? So for example, if we were to create an integer instance for monoid, it would look something like this. So actually integer has multiple monoid instances, but this is the addition instance, right? So we have empty, which is 0, right? And to combine two monoids, we can add them. And this is pretty useful for a reason I'm about to show you. So let's say we want to like sum a list of integers, right? So what we usually do, as functional programmers, we don't use like a while loop or something, but we use this fold function, right? Or reduce in other languages. And it takes a seed. So the seed usually, when you want to sum a list of integers, is 0. And then we'll just add all of the integers, right? And we need the seed because the list might be empty. And if it's empty, then we'll have to return something, right? So otherwise, it would have to throw an exception because what can you return, right? So this is sum on a list of integers, but we can do the same for a list of strings with an empty string and string concatenation, right? And we could also do the same thing with a list of sets and then having an empty set and using set union, right? So, and maybe you've seen a pattern here, right? So we have this in the full left, we usually use like an empty thing as the first parameter, and then as a second parameter, we want to combine two things, right? And if you can add 1 and 1 together, you get this, which is the sum function that actually takes a monoid. And this works on any monoid. So actually, like strings, integers, and sets are all instances of monoids. They all have monoid instances, and they're all defined in the cats library. So if you're using that, you can totally use this last function and just it will just work. And it uses this monoid t.empty for the seed, and then it uses the combine function we saw before to combine the individual elements of the list. And this might look a bit weird because, like, what is this, right? So monoid t.empty, and this is actually one of the features of type classes, is that because type classes don't because they operate on the not on the value but on the type itself, we can actually associate an empty value to a type, right? So for example, monoid for int.empty is 0, and monoid for string.empty is the empty string. So because we don't operate like on a class or whatever, we operate on the type, we can call these things for this sum function. And this works. This is one of the features of type classes that's pretty cool. And yeah, so another really, really cool feature of type classes is that we can do something called implicit derivation, which is not the same as type class derivation, but finding names for these things is difficult. So what we can do, for example, if we wanted to create a monoid for option, you would have to, like, the empty case is easy, right? So you can just use none. But if you have an option of integers, we could use plus. But we want to define monoid that works for any t, right? So for an option of any t, like we see up there. And what we need to do is actually say that how can we combine any t's? And we already have this monoid type class. So what we can do is we can basically induce this implicit, right? So what we can say is that I can give you a monoid for option of t if I also have a monoid for t, right? So that makes absolutely sense. That makes really a lot of sense. And then combine is just like if both are true, then combine them, and then you get this combined option value, right? That should make sense. But this is a feature that you really can't do when you use like standard OOP interface. And this is what makes type classes really, really powerful. So, I mean, you all know type classes, so this shouldn't be news to you, but yeah. Okay, so very quick, type classes versus subtyping. Type classes give us operations on types instead of on values. I said that a lot. And this comes in handy because type classes like monoids need to have like this empty method that works on a type. And we wouldn't want to define it for every instance because it doesn't make any sense. And last part, we can use these type classes to derive instances for data types that might hold other data types when they also have instances, right? So option of t is a monoid when t is also a monoid. So we can build up these trees, and we can, in cats, there's actually like a lot of implicit induction we can do. So yes. So, and actually monoids are really cool because they're everywhere, right? So this is the function monoid, right? And it gives us a monoid whenever a function return type is also a monoid, right? So the empty is just a constant function that goes from anything to the empty value of the monoid. And to combine two functions, we just run them both, and then combine their results. So that's pretty simple. But now we have a monoid for a to b, and we can use that for any a to b, or any a to b where b is a monoid. And we can also do this for tuples, right? So if a and b are tuples, it's pretty easy to imagine how we can combine two tuples when both of them are able to be combined. And we can, of course, also create this empty because we have empty values for both. Right. And what else is a monoid? We have this either monoid, we have a map monoid, right? So if we have two maps, we can combine them. If they have the same key, then we can combine the values of those keys. And future is also a monoid. So if you have two futures, we can combine them so that they will both be run, and when they're done, we can combine the resulting values. And there's many more that I couldn't possibly list because it's too many, right? And why is this useful? So I'm gonna give you a very small example that was very inspired from my colleague Marcus. So basically, what we have is we want to define like a small application that reads a text file and gives us back like some statistics, right? So we define the step function, and we have like a data value that basically just reads in our lines, like text data as lines, and then splits them all up into words, and then maps them to this thing, which is a tuple of two integers and a map of string to integer, right? And they will represent the number of characters, the number of words, and also the occurrence of each word, right? So if we apply this step function to a word, we will get a tuple of 1, and then of the word length, and then a map of word to 1. And then if we combine tuples of these values, for example, we have like hello and world, the combining tuple will give us the number of words, which is 1 plus 1 is 2, the combined characters, which is hello length plus world.length, and then a map of hello to 1 and world to 1, right? And if we apply this to all of the words in our text, we actually get the full word count, the char count, and the occurrence of each word, right? And this is pretty easy. We need to do like this monoid.empty, and we need to add this really big type. And also I kind of cheated, and I added a symbolic operator for combine. So this plus thing with the TIE fighter looking whatever, that is actually just an alias for the combine, for just giving it a symbolic operator. And well, this is cool, but it's also not that great, because we need to like define this monoid empty thing manually. So I don't know, maybe you can do better. And actually we can do a lot better. We can just shortcut this into this. And combine all is just an alias for doing exactly that. So if we know that our data is a list of a type M which has a monoid, we can call this function called combine all, which is provided by cats, and it will be exactly equivalent to folding over it with the empty type and then applying this combination operator, this monoidal combination operator. Yeah, and I think that is a very succinct, pretty cool thing you can do with monoids, and that's just scratching the edge. Right, and of course, there's no monoid talk without talking about laws. Laws are very important. Monoid is actually a mathematical term, and if you just define anything as a monoid, it has to actually, it also has to be a lawful monoid. And these are the laws. We have this associativity, which I personally learned in like 6th grade, and there was like, why is this ever useful? And now it's like, oh my god, associativity is the most useful thing ever. So this is pretty funny, actually. But yeah, so it basically means that the combining order doesn't really matter. So x plus y and then plus z has to be the same as x and then first combining y and z, right? So this is just associativity. It's fairly simple, but it helps us a lot, which we'll see later. Then we also have right identity, right? And this just means combining something with its empty value will still be the same, right? So combining a string with the empty string is still going to be that string. Or combining a number with 0 is still going to be that number, right? And the same goes for left identity, so it doesn't matter. Right? So the identity has to commute there. Okay. So why do we need this? It's actually really useful because it allows us to give us a lot of transformations that are really, really cool. So for example, if we have this, right? So this is a list of 6 types, which we're all combining. And because of our monoid laws, we can do something like this, right? So we can actually group them in certain places. And this is cool because, as we'll see later, we can also group them by a constant number, right? So now we have 4 groups that we can all do, that we can all compute individually and, more importantly, independently, right? So at the top, you would say, okay, I can only do this sequentially, but because we have associativity, now we have 4 completely independent computations that we could potentially run in parallel. Right? So we can write a fully parallel version of something like fold. And that actually makes this really, really powerful. And I've got a quick example how something like that would look. It's not like, doesn't work fully just like this. But for example, if we have a list of some A which has a monoid, then we can basically group it into groups of our available processors. So if you have like 8 cores in our computer, we could have a list with groups of 8. And then what we can do is we can map those in parallel and then combine those inner groups to get back a list of A's, which are the combined groups. So now we should have a list of 8 elements with the individual values. And then we can just call combine all to get the final result. And we'll have actually completely parallelized our fold. And that is what I think is really, really cool. And this is what monoids give you because of associativity and identity. Right. So let's talk about functors. Who here has heard about functors or who knows functors? Oh, that's a lot of people. You guys are great. Cool. So functor is another type class, and instead of taking a normal value of type T, it takes what we call a higher kinded type as a parameter, and this is represented as this f open bracket underscore open bracket close bracket. Right? And what this means is that in order to become a fully applied type, we actually need to give it a type, right? So f itself is not like a type we can use, but we have to give it a type to become a type. We also call these type constructors, right? An example of this is for something like list, right? So list itself, you can't give us a value of list. You have to give us a value of list of something, like list of integer, list of string, right? And so this is the same thing, just in an abstract form. And so this functor type class basically abstracts over the map function, and I think most of you here have used map. I really assume so, and it basically allows us to give us a value of some type f of a and a function of a to b, and then we will get an f of b. And examples for this, of course, are list, option, either, vector, or future, and there's many, many more. Almost all, very, very many things are future. And yeah, these are just some examples. I think most of you, this makes a lot of sense. So let's talk about something called monoidal functors. So monoidal functors basically combine the parameters of monoids with the parameters of functors. And so, for example, right, this is a monoid, right? So we have an A and an A, we combine them to get a new A. But we might also have like an f of A, right, like we saw with the option. Option of A combined with option of A is also an option of A using simple monoid. But what if we have something like this, right? We have this f of A and f of B, and now we want to combine them. For example, an option of int and an option of string. But what would that return type be? And we can't use the normal monoid combine because it expects the types to be the same. So we need something different here, and I use this weird operator thing. So does anyone know what could be the type, the result of this? Either? It could be either, but I'm actually going to talk about tuple, right? So it would probably have both, right? So if you have an option of A and an option of B and you combine them, you could get like an option of both, right? That's the most common operation, I think. And yeah, and this is essentially what monoidal functors can give you. And we'll see right here. So this is the monoidal type class. It extends functor and it adds these two methods. And it takes, one is the product, which looks a bit like combine, but as I said, it has this tuple thing going on. And it allows us to create, to combine two type constructors into a new type constructor, but it will take the values inside those type constructor and combine them inside of a tuple. And it also has this pure method, which is very similar to the monoid empty method in that it just lifts a value into this context and it doesn't actually take a value of inside our f context, inside our f type constructor. And examples for this are like we talked about, the option monoidal. And of course, we also have something like future. And yeah. So what can we do with this? So who here has used future.sequence? Man, you guys raised a lot of hands. This is great. Okay, cool. And future.sequence is a really, really useful function. Basically what it does is if you give it a list of future, it will run all of them in parallel and return you a future of all the results. And that's pretty cool. So what can we do? Maybe we can generalize this. So here we have this, the same function again. It takes a list of future of A and returns a future of list of A. But let's try to abstract out this future and try to put in something else. And what I did here is exactly that. We took, instead of taking a list of future of A, we take a list of f of A. And instead of returning a future of list of A, we return an f of list of A. And this is the most simple implementation. We basically fold over the list. We lift an empty list into our monoidal f, right? And then that is the seed. And then to combine these, we actually call this product method, and then what we get back is an f of tuple of A and list A, And then because we also have map, we can just turn that into an f of list of A by calling map and then combining the A with the list of A. And then we get back an f of list of A, which is also our result type. And this basically gives us a way to combine all of the f of A's, which are in our original list, and give us back an f of list of A. So basically, it's able to turn this list of f of A inside out, and that is pretty cool. And if you saw the monoid sum function a bit earlier, it actually looks pretty similar. Like this. So this monoidal f dot pure is basically, like I said, it's the higher kinded functor version of monoid dot empty, and this product function is basically like the combined function that monoids have. So this is like the functor version of the monoidal sum function or combine all function, right? And there's actually some syntactic sugar, so we don't have to do this product and map, so we can actually do it in one step using cats, and it just takes like we can just have a tuple of our two types, and then call this map n, which is equivalent to product and then map, right? So this is just syntactic sugar, and I think it looks a lot nicer that way. Yeah. So this is future.sequence, but there's also future.traverse, and we can do the same thing here. So we have traverse, which takes a list of A, and then a function from A to future of B, and returns a future of list of B. And actually, the implementation to generalize this is really, really similar. We just need to apply this f function before actually calling this map n function. So what we do right here is, if you look at this and then this, I can't show it side by side really well. Should have thought about that. But yeah, instead of getting an f of A as our first parameter inside the fold, we get an A, and to lift it to an f of A, or an f of B in this case, we just call this f function. Right, so this is really similar, and actually, traverse is basically like a shortcut or a more efficient version of calling map and then sequence, right? So whenever you see a map and then sequence in your code, just inline it to traverse. It will be faster and cooler. Okay, so and another cool thing is that the laws for monoidal are actually the same as the laws for monoid. So we have associativity. So if we first call the product function on FA and FB and then on FC, it should be isomorphic to FA and then first using product and FB and FC, and then calling product and FA and the product of FB and C, right? And the same is true with the right identity and left identity. So if we call this pure function and then use product, it will have to be isomorphic. It can't have any effects on the actual value, right? So this is another similarity to monoids. And yeah, I have a very tiny secret. So I call this thing monoidal so far, but in all of the libraries out there in Haskell and Scala Z and Cats, it's always called applicative, and that is short for applicative functor. But in order to show you this similarity, this relationship, I wanted to basically introduce it to you as monoidal. So if you already knew about applicative, I might have confused you, and I'm sorry about that, but from now on we'll use applicative. So, okay, cool. So, next up is this thing called the foldable type class. So far, we've used list everywhere to have like our basic collection type, but what about some things like vector, stream, or something like option, which is basically like a list with a single element or none, right? And that's what this foldable type class does. So this foldable type class has a few methods. One of them is foldMap and the combine all function we saw before. And foldMap takes an abstract f of A, right? So this could be list or vector or stream, and then it takes a function from A to M, and M has to have an instance of monoid, as you can see there. And then, because we have a monoid and a list, then, or something that is list-like, we can fold it into a single M value. And combine all is basically like a shortcut. So if you already have a monoid inside this F, right? So again, oh, I didn't include it here, but yes, again, combine all is just fold map with identity. And of course, instances for this is a list, right? We have a list foldable, a vector foldable, an option foldable, things like that. And now the really cool part and the title of our talk is traverse. And the traverse type class basically generalizes what we did before with future in an even more abstract way. So this is traverse. It extends both foldable and functor. So we call them traversable functors, or just traverse for short. And it has this sequence function that looks a lot like future.sequence, but it's instead of having like instead of having future or list, we have just this T and F, right? So basically this T represents our traversable type, and that can be something like list, vector, and stream. And F represents our monoidal or applicative type, which is some kind of effect like option or future or something like that. And basically from the types here, we can see it takes an T of F of A and returns an F of T of A. And that's just, and you can really see here that it's just basically turning things inside out. And that's the intuition that really helped me. And of course, we also have the traverse function, which is very similar again. It takes a T of A and a function from A to F of B and returns an F of T of B. Right, so that's cool. We have instances for vector, we have instances for option. We can also do something crazy like have instances for either with a string, right? So either with where the left type is a string is either a string or an A, and basically it's like an option where the none type is just some string. And of course we can then of course if we can define an instance for option, we should also be able to find one for either. And so we actually had to use this this type alias, but we can actually do a little bit better because we don't want to force like the string on the left-hand side. We want it to be any E type. And to do that, we need something called kind projector or something even more ugly called type lambdas. But basically, this means that because either takes two type parameters, we have to use this question mark to turn it into a type constructor that only takes one type argument. Right, and this is how that works. Right, okay, cool. So what can we do with this? So, for example, we can turn a list of future into a future list of A. That is the future.sequence use case. But we can also do something like stream of option of A to option of stream of A. We can turn an either E or IOA into an IO of either E and A. And we can do this for dozens of different combinations, right? So every time you have a traversable type, which can be stream, list, vector, option, either, or the applicative type, which can be option, future, IO, but also vector and list and whatever. So we have dozens of different combinations we can do, and the only thing we need to do is define a traversable instance and an applicative instance, and we can immediately get all of these implementations for free. And that is a really, really cool thing. And one of my favorite, actually, traverses is over using something like validated NEL. So where's the word of validated? Does anyone know what that is? Okay, that's cool. Less people, but still a lot. Okay, I'm going to explain it to you. But basically what this does is it's just the same type, the same shape, right? So we have a vector of validated error A, and we turn it inside out into a validated NEL of error and vector A. Right? It just has another type parameter, type here error. But apart from that, it's the same shape of turning these nested type constructors inside out, right? I hope that makes sense. Right, so what the hell is validated NEL? That sounds weird. So in cats, we have this thing called validated, and basically it represents either a valid case, which has a value of A, or an invalid case, which has a value of E. So it's basically like it's isomorphic, or it's similar in shape to either. And validated NEL is just a type alias for validated with a non-empty list of some type E as its left type, right? So this validated NEL of E and A will either return a non-empty list of type E or a value of type A. And this is actually a fully formed applicative or a fully formed monoidal. And what this allows us to do is to create a function that called validate. So for example, if we want to have like, we still have like some text and we want to parse it to like something like a user class, which might be some data class, right? And to parse it, it might return a list of errors, or it might return a valid user, because it's a string we can't really know. So we have this validate function, where I'm not going to show you the implementation. And now what we can do is, if we have a bunch of lines that we want to parse as users, we can do this using traverse. And very simply speaking, we have this lines variable basically is a list of string, and now we call traverse using this validate function. And if we were just to call map first, we would get a list of validated NEL of error or user. And now if we were to then sequence that, turn it inside out, we get this type validated NEL error or list user. So basically what this gives us is either we will get a non-empty list of errors, or we will get a list of users. And this is just a single line for validation with error accumulation, and that makes it really, really powerful and really cool in my opinion. Okay, so still not convinced. So this is kind of a joke, but so because this question about how to turn one thing into another comes up so often, I couldn't really let that go. So what I did was I looked in my Stack Overflow history of like the last 6 months and looked at all my answers, and I picked all the questions that could be answered with like, oh, that's just traverse. So we have this. So how do I turn list of either t future AB to either t future A list B? And if you like think away all this either t AB thing, this is just turning it inside out. So this is just sequence or traverse. And of course here, how do you turn a list of IO into an IO of list? Sequence. How to turn an either error option whatever sequence. How list a Kleisy to Kleisy list sequence. Combine valid uses of seek validated NEL. So he has this seek validated non-empty list string, my string, into validated non-empty list. That is exactly what we just did. That's just sequence. Come on. So, okay, I've got 5 more minutes for something called semigroups. And semigroups are really cool as well. That's just because monoids are cool. So this is a semigroup, and it looks a lot like a monoid, except it doesn't have this empty value, right? So it's just, it allows us to combine things. And yeah, actually semigroups just describe like an associative binary operation. That means semigroup has only one law, and that means that this combine function has to be associative. Because it doesn't have an identity, it can have the right and left identity laws. So this is cool, and actually if you look at the if you look at cats, you'll see that something like monoid doesn't actually have a combine method. It actually extends semigroup and gets, the combine method from there. So we have this subclass relationship again. So monoid extends semigroup. And why are semigroups cool? Well, who has ever gotten this, right? So not the first thing, but unsupported operation exception empty.max. Who's gotten this error before? Yeah, okay. Well, I expected more, but that's fine. So what happens is that in the Scala collections, that if you call, you can call this max operation, which will give you the maximum of any collection. It will fail if the list is empty or the stream or vector is empty, and basically just say, well, yeah, throw it one time. And that's never what we want. What we usually always want is to have like guarantees at compile time and never fail at runtime, right? And the same is done with reduce, right? So reduce is like the version of fold where we don't give it a seed. And of course that fails if the list is empty. And yeah, what we can actually do though is we have this cool non-empty list in cats. And it gives us a way to only construct lists that are non-empty, right? So if we call this thing non-empty list with open parents, close parents, it actually won't compile. We'll throw an error at compile time and say that, hey, you need to give me a head, and then you can do whatever. So, and because this non-empty list gives us this guarantee that it's non-empty, as it's called, we can actually very safely call maximum on it. And actually, like, maximum is implemented in terms of what is called a semigroup, right? So if we have, there's this thing called max semigroup, and basically that just means that if we combine two values, it will always take the maximum of the two values. So if we traverse a whole list with this maximum semigroup, it will always give us the maximum value. And because there is no empty value, you can't create a monoid for max. You have to use the semigroup, and to use this maximum function, you have to actually make sure that this list is non-empty, so that you can actually use a semigroup instead of a monoid. Right, and of course we can also call reduce safely on a non-empty list. And as a last bonus slide, I have semigroupo functors, which are basically like monoidal or applicative functors without the pure type, right? So semigroupal are like semigroup to monoid. They don't have an empty. They don't have semigroupals don't have a pure. And of course, monoidal then extends semigroupal. And because I already told you that's a lie, we have apply and applicative instead, right? So apply basically means that we only have this product function, and we don't have this pure. It's added in the applicative. And why do we need that? Well, basically, you can also traverse over things that don't have a pure function. If you use this apply, if you have a non-empty collection, and as an example, you can try to create an applicative for something like map, and you might run into errors immediately, because if you want to write an applicative instance for map, for how do you create a value of map kv if you only have a value of v, right? If you want to insert something into a map, you need to give it both a key and a value. You can't just give it a value. So this is basically unimplementable, and that's why applicative can't have. That's why map can't have an applicative instance, but what it can have is an apply method. And yeah, this works, and we can actually use a non-empty list to traverse over applies, over instances that use apply instead of applicative. So that's it for me. Conclusions, very quick. Today we learned about monoids, functors, applicatives, and foldables. And of course, we also learned about non-empty lists and validated. And all of this can be found in cats. And yeah, we learned about the really cool power of traverse. So if you don't know what to do, just call traverse, see if it compiles, then usually your code is fine. Okay, thank you very much. I hope this was a good gateway drug. So you should all check out cats. Yeah, thank you very much for listening. My name is Luka. You can find me on Twitter. Yeah, on GitHub. I'm also active on Gitter on the Cats channel, so if you ever have any questions, just feel free to ask. We're very friendly and want to convince you to use it more, so we try to be as nice as possible.
Yeah, thanks a lot, Luka.
Thanks.
Although we are actually at the end of the talk exactly, since we're going to lunch break now. If there are urgent questions now, I think we can take 2 or 3 questions. But if you're hungry, you can also already leave the room. But if they're okay.
Just a silly question.
Sure.
Why do you annotate the type class with type class? So what it gives?
Right. So this at type class annotate. Yeah, this is simulacrum. Basically, what it gives you is syntax, right? So, for example, in the let me just skip to the beginning. Here in this show thing, right? We call this. We call this. God, why is this there? Okay, this t.show. So basically, what it allows us to give us syntax, right? So because if you were only to define it without this at type class annotation, you couldn't get this nice syntax. So what we would have to do instead of calling t.show, you would have to do implicitly show of t.show and then in parents t. So it's basically just to give us the nice syntax we're used to when using Scala in general. Yeah. So this inline syntax most of the time, yeah. And it's really cool. You should, like, if you want to write your own type classes, Simulacrum is pretty nice, yeah.